Let's study more in depth the kernel and image of a linear transformation between arbitrary vector spaces, right? Remember, we studied these notions in depth for transformations of Euclidean space. But once again, we're going to generalize our understanding to arbitrary vector spaces. And so let's remember here, if we have a linear transformation T from V to W, then there are two very important sets that we can talk about here. We can talk about the kernel, which the kernel of T is given by, well, we write it ker of T, and it's defined to be the set of all vectors V in V such that they map to 0 under the transformation T, right? So we're looking at everything that gets mapped to 0. We also have the image of T, right? And one thing you may notice is that this is a subset of V, right? The kernel belongs to the domain, right? The kernel is contained in, it may or may not be a subspace, but it's contained in the domain. The image of T may or may not be a subspace, but it's contained in the codomain. So what is the image? We write M of T for the image of T, and this is defined to be the collection of all vectors W in the codomain W such that there exists a V in V with W equals T of V, right? And so it's the collection of all points that are mapped to under these this linear transformation T. And I said that it may or may not be a subspace. That was slightly a lie because we have the following proposition. Whoops, getting ahead of myself to the proof. So here's the proposition. It's that the kernel contained in V and the image contained in W are necessarily subspaces. So here you can see what I'm saying is that the kernel is a subspace of V and the image is a subspace of W. Let's prove this. Remember, to prove this, what we need to show, we have this subspace criteria, right? So recall, I'll just kind of recall what we need to prove here. X is a subset of Y if for all, say, x1 and x2 in X, this implies that ax1 plus bx2 is also in X for real valued scalars A and B and R, right? This is what we need to show that X is a subspace, right? So let's do that for the kernel, and then let's do that for the image. So first, for the kernel, let's say V1 and V2 are two elements of the kernel of T. Well, what does that mean, right? That means that T of V1, so i.e. T of V1 is equal to 0, and T of V2 is equal to 0. We need to show, right, for any two elements, we need to show that all linear combinations of these two elements still belong to the kernel. So let's look at A V1 plus B V2, right? So if the question is this an element of the kernel of T? Well, we don't know. How do we show that something's in the kernel of T? Well, we apply the transformation to it and show that the result must be 0, right? So let's look at T of A V1 plus B V2. T is a linear transformation, so this is A times T of V1 plus B times T of V2, which then we know V1 and V2 are in the kernel. So this is going to be A times 0 plus B times 0, which is 0 plus 0, which is 0, which implies that AV1 plus BV2 is an element of the kernel of T, given that V1 and V2 were elements of the kernel of T. So therefore, the kernel of T is a subspace of V. Cool. Let's do the same thing for the image, right? What are we doing now? We're starting with W1, W2 contained in the image of T, and we want to show then that AW1 plus BW2 is also in the image of T. Well, how do we show this? We start with A W1 plus B W2 and somehow argue that this is equal to T of something in the domain, right? We have to show that this element here is mapped to from some element of the domain. Well, W1 and W2 are in the image, which means there exists a V1 and V2 respectively, such that AW1 is equal to, well, let's write it up here, right? This implies that there exists V1, V2 in V such that Wi is equal to T of Vi, right, for I being 1 or 2. So this is A times T V1 plus B times T V2. Those that V1 and V2 exist because W1 and W2 are in the image, right? Next, we have that T is a linear transformation. Therefore, this is T of A V1 plus B V2. But this implies that AW1 plus BW2 is in the image because we found an element in V that maps to AW1 plus BW2. So this implies that the image of T is also a subspace. But it's not a subspace, right? The kernel is a subspace of V, right? Maybe I'll just write contained in V, whereas the image is a subspace of W. So that's a very important distinction there. Awesome. Okay, let's look at an example of calculating the kernel and image for a linear transformation. So let's consider, well, here's an example. Let's consider T from P1 to R given by T of P of X is equal to P of 1, right? For all P of X contained in P1. Remember, what is P1 here? This is the polynomials of degree at most 1. So this is AX plus B such that A and B are real numbers. Now we want to find the kernel and the image of this transformation. Well, let's think about the kernel here, right? The kernel of T is going to be the set of polynomials P of X such that P of 1 equals 0, right? Because the output of this transformation is P of 1, and so the kernel is going to be polynomials of degree at most 1 who have a root of 1, right? So what does this mean, right? This means, this means polynomials AX plus B such that, well, so really here, we're looking at P of 1, right? And so if we have for an arbitrary P of X equals AX plus B, well, that implies that P of 1 is always of the form A plus B, right? And so this means the kernel of our map is polynomials AX plus B such that A plus B is equal to 0. Because if we set P of 1 equal to 0, well, then we would be setting A plus B equal to 0, right? Plug in 1 for X, you get A plus B, i.e. the kernel is polynomials of the form AX minus a, right? Because this implies that b would be equal to negative a. And maybe I should be more precise here. This is ax minus a for a in the reals. Well, this is, as a set, you could think of this as a times x minus 1, such that a is a real number, which implies that the kernel, so this implies that the kernel of t is equal to, well, really it's the span, because you see x minus 1 spans the kernel here. Right? Any element of the kernel is just some scalar multiple of the polynomial x minus 1. And so this is the kernel of this linear transformation that takes a polynomial, and to each polynomial, it assigns it the number p of 1, right? You just evaluate that polynomial at 1. What about the image, right? The image of t is going to be, well, it's going to be the set of all points p of 1, right? So basically it's p of 1 such that p of x is an element of p1. But what is p of 1, right? If polynomials in p1 are of the form ax plus b, well, then that means we just have the collection a plus b such that a and b are real numbers, right? What is this collection? Well, if you let a and b vary through all of the real numbers, the sum a plus b varies through all of the real numbers, which means that the image is just R. So we have that the kernel was the span of the polynomial x minus 1, and that the image is the real numbers. What do you notice here? Well, so we calculated the kernel and the image, which is what we wanted to do, right? You may notice the codomain of this map was the real numbers, and it's also the image, right? And so the codomain equals the image, and if you remember, this implies that t is surjective. We weren't asked to state that or show that, but it's worth noting. Anytime you calculate the image and you get that the image is the same as the codomain, well, then you know that your map is onto or surjective. Let's look at another example. Let's look at the transformation from M to 2, so the space of all 2 by 2 matrices, to R2, given by T of A, B, C, D is equal to A minus B, C plus D, right? Say we want to find the kernel and image of this map. Well, let's do that, right? What is the kernel? The kernel of T is going to be the set of all vectors A minus B, C plus D in R2, such that A minus B is equal to 0 and C plus D is equal to 0, right? Because if it's in the kernel, that means it maps to 0. And if it maps to 0, that means this should be equal to 0, 0. And if that's equal to 0, 0, we should necessarily have that A minus B is equal to 0, and then C plus D is equal to 0. So this means, in particular, that A equals B and C equals negative D. Let's give A the parameter S and C the parameter T. Well, then that makes the kernel the set of all 2 by 2 matrices given by, right, sorry, this should not be, that is my mistake, I apologize. This should be A, B, C, D contained in M2, 2, right? Duh, because the kernel is always in the domain. That was a mistake. But we've set the image of that equal to 0, right? When the image is 0, like when the image of an element is 0, it belongs to the kernel. So then the kernel is going to be here. We have A equals B equals S. So we have like S, S, and then C equals T and D equals negative T. So this is for S and T in the reals, right? So the kernel is matrices of this form. We can write that as S times 1, 1, 0, 0 plus t times 0, 0, 1, negative 1. And if that's the case, that means the kernel of t is spanned by these 2 by 2 matrices, 1, 1, 0, 0, and 0, 0, 1, negative 1. And so this was how we found the kernel, right? You calculate what what matrices map to 0. And well, the matrices that map to 0 are precisely those that satisfy a minus b is equal to 0 and c plus d is equal to 0. We found the solution to that system given by a equals b, c equals negative d, threw in the parameters, wrote the parameters in terms of linear combinations of other matrices, and used those to define the kernel in terms of some basis, right? This is a basis for the kernel now, because it's pretty easy to verify that those two matrices are linearly independent. You can also verify, well, this up here verifies that it spans. So that's the kernel. And what about the image, right? Well, now the image of T is going to be the collection of all vectors A minus B, C plus D in R2, right? This is how you would find the image, because you're looking at any vector of the form here, right? Well, that means we can write these out more explicitly. Vectors A minus B, C plus D can be expressed as a linear combination as follows: A times 1, 0, plus B times negative 1, 0, plus C times 0, 1, plus D times 0, 1, right? And so here you can see that the image of T is then spanned by these 4 vectors here. So we have 1, 0, we have negative 1, 0, we have 0, 1, and we have 0, 1. This is very clearly a linearly dependent set. If we reduce this to just linearly independent elements, you can see this is the span of 1, 0, 0, 1, right? Which is R2. And so this means the image of this transformation is R2, once again implying that T is surjective, or onto, because the image we calculated is also, it's the same as the codomain. Cool. Next, let's look at a very important theorem. Let's let V. So when I write, I'm going to start using this notation here. When I write V to the n, this is a vector space with the dimension of V equal to n, right? Just like we write when we say Rn, well, that's the real numbers, but understood to the dimension n, right? Or the nth dimensional real numbers. The same will be true for vector spaces in general here. So let's say T is a transformation from an n-dimensional vector space V to an m-dimensional vector space W. Then n, so the dimension of the domain, is equal to the dimension of the kernel of T plus the dimension of the image of T. And if you'll remember, we have the following definitions, that the dimension of the kernel of T is called the nullity of T. We write null T, right? In words, this is equal to the nullity of T. We also write this as just null T. And then the dimension of the image of T is equal to the rank of T, which is equal, we denote this as rank T. Right? Okay, cool. So what does this theorem say? And this is the rank nullity theorem. Very important theorem. I would not be surprised if I just ask you to state this theorem on the final. I'm not saying I will, I'm not saying I won't, but I'm saying it's important enough that it could happen. So The theorem says that for a transformation T from Vn to Wm, the dimension of V is equal to the rank of T plus the nullity of T. Very, very important. I want to emphasize the importance of this theorem here. Okay, I think what I want to do is I want to do one more example here, and then we'll move on to looking at the matrix of a linear transformation. Well, before we do the example, there's one more thing, or a few more things I want to say, actually, I believe. So we have this theorem that says, like, let's consider W to be a subspace of Vn. So this is a subspace. We have V is isomorphic to W if and only if the dimension of W is also in, right? So if you have a subspace that's of the same dimension as the vector space that you're looking in, well, then that's actually the same vector space. And the reason I state this theorem is more for the corollary we get, which is for, let's consider T from Vn to Wm here. T is, and then we have a few statements. It's 1-to-1 if and only if the kernel of T equals 0. And it is onto if and only if the rank of T is equal to M, okay? And these also follow from the rank nullity theorem. So what this example is going to do is it's going to be looking at an example we've considered previously. It was an example showing that, so here, let's recall this map. It was S from P2 to M to 2, given by S of A x squared plus bx plus c is equal to a plus b, a plus c, b minus c, and b plus c. What we wanted to do, and what we're going to do again, is show that S is 1-to-1, but not onto. And how we did this the last time was we just compute explicitly. Right? We showed the injective and surjective properties explicitly and showed that it was satisfied in the case of injectivity, but it failed in the case of surjectivity, right? Remember, so like for injectivity, it's injective if and only if T of 0 or T of V equals 0 implies V equals 0. Well, that's really this statement, right? You think about what it means. If you have T of V equals 0 implies V equals 0, that implies the only element of the kernel is the additive identity 0. That's exactly what this is saying here, right? And so instead of having to show this, however, we can just compute the kernel as a subspace, see that it's purely 0, and then we're done. Similarly, right? The rank of T being M means, right? So these statements are the same. This statement is the same as saying that the image of T is equal to the codomain, right? Because what do we have, right? Remember, we know that the image is a subspace of W. But if the image is of dimension M, then by this previous theorem down here, then they're isomorphic. So what we're saying, what all this is saying here, that the rank of T is M, is saying that the image is isomorphic to the entire codomain, right? And so we can compute and determine surjectivity and injectivity just from kind of a subspace point of view, right? Not having to like get our hands so dirty and try to find a counterexample to this criteria or show for every element there exists this other element, right? Like we don't have to get our hands so dirty. when we can just kind of understand the subspaces of the domain and the codomain. So let's prove this example that we've already looked at, but now let's do it in the context of this corollary here. So we want to show that it's 1-to-1. So let's calculate, right? We need to calculate the kernel of S. And if we show that it's just the 0 element, well, then we've shown then we've shown that this is an injective transformation. What is the kernel? The kernel is going to be polynomials ax squared plus bx plus c such that, and then the kernel is where things are equal to 0. So we're setting this 2x2 matrix equal to 0. If we do that, we're getting the system of equations a plus b equals 0, a plus c equals 0, b minus c equals 0, and b plus c equals 0, right? This is what the kernel looks like. We can take this system of equations, set up the following system of equation or augmented matrix for that system, right? It's a plus b equals 0. So we have 1, 1, 0, 0. And then we have a plus c equals 0. So 1, 0, 1, 0. I'll just go ahead and fill out the rest, right? You get the idea. We're setting up an augmented matrix for that system that determines elements of the kernel. So 0, 1, 1, 0. You put this into reduced row echelon form, however you like. Good practice as the final approaches. And you get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, which implies that A equals B equals C equals 0, which implies that the kernel of S is equal to 0x squared plus 0x plus 0, which is just 0, which implies that S is 1-to-1. Awesome. Okay. How can we show that this map is not surjective, right? Well, it suffices to show that the dimension of the image or the rank is not the dimension of M22, right? And remember, the dimension of M22 is equal to 4. So to show S not onto, we want to show that the rank of S is strictly less than 4, right? How can we do that? Well, let's look at what the image of S is. The image of S is the set of all 2x2 matrices of the form A plus B, A plus C, B minus C, B plus C, which we can write this matrix or these matrices as the following linear combination, right? That would be like A times 1, 1, 0, 0 plus B times 1, 1, 0, 0 plus C times 0, 1, negative 1, 1, right? And that's it. So the image is then spanned. This implies that the image of S is spanned by these three matrices, right? Because we can write any matrix in the image as a linear combination of the three matrices written below, which means that the image is equal to the span of the following matrices: 1, 1, 0, 0, 1, 1, 0, 0, and 0, 1, negative 1, 1. It is not hard to show that these are linearly independent. Therefore, this is a basis, right? Which implies that the dimension of the image of S, which is the rank of S, is 3. 3 is less than 4, which implies S is not onto. Okay, so there's an example of showing how you can compute surjectivity and injectivity purely from like this rank and nullity standpoint, right? Okay, so I think I'll stop here. There is one video left of new lecture material, and what I'm going to talk about is how can we understand the matrix of a linear transformation between arbitrary vector spaces?